Hey, so in this video here, we're going to focus mainly in 1.3. Place my dot back there. We're going to focus in 1.3, and if you think about the last video where I mentioned when you work with linear equations, it's much easier to work with them when they are solved for the variable y. Let's take a look at y again. When you have your equation solved for y, one, we can understand, we can now visualize, why do we call this variable the dependent variable? Why is the x variable the independent? Independent means you don't have to worry about anything, right? You are free to choose. You have that free state of will. This y here, though, is dependent upon x. Take x, multiply it by 4, add 7, you'll get y. So there is a dependence there. For this reason also, when we think about working with functions and working with these equations, we want to be able to work with them much easier, and we want to be able to graph them much easier. You get both of those when you work with it in this form. This is called slope-intercept form. Slope-intercept form means that we have the equation solved for y, and it takes on a particular sort of set here. Notice there's two terms, right? We have this term here, 4x, and we have this term here, which is a positive 7. So a linear equation or a linear function is only going to have two terms at most. It has a max of two terms. And in this case here, the first term that includes the variable x, this is going to tell us what the slope is for our line. Remember, the slope is going to tell us how the variables are changing with respect to one another. In college algebra, we talk about it as the measure of the steepness of the line. That's exactly true. But we're working with applications here in applied calculus. So what does that steepness mean? It just means, well, we're looking at an XY graph, right? We have our independent variable and we have our dependent variable. How is the dependent variable changing with respect to the independent? So we're going to talk about unit production. How are the units and the cost changing with respect to one another? And so that's really what the aim is. Let's not think about it in terms of steepness of a line. Let's think about it in terms of two variables acting on one another, and we're seeing how they change as we move along our x-axis. So y equals mx plus b. And we ask ourselves, why is it much easier to work with it in this form? Well, first and foremost, it's easier to graph. If I know that my slope here is 4, and if I know this number here, remember, what does this b value tell us? Slope intercept. M is the slope. The intercept here, this is the y-intercept. It's the y-intercept because this number here tells us what the y-coordinate is. So in this case here, our y-intercept is 0, 7. With this information right here, I have more than enough to graph. It's all about using the information that's given to you to graph and to interpret. If you have to find the other information, well, again, take what's given to you and work with that. If this is all I'm given right here, I'm given the equation. What else do I need? I now need to graph it, and I need to use it to interpret my information. So the first thing we want to do here, as soon as we have the equation, is graph it. Now, what have we been saying? Graph the x and y intercepts, you have your graph, right? So going in here and plugging in 0 for x, you'll find your y-intercept to be 0, 7. And going in here and plugging in 0 for y and solving for x, you get that the x-coordinate is -7/4. And we can graph those 2 points and call it a day, where our x-intercept here is -7/4, 0, and our y-intercept here is 0, 7. That's all we need to do, find the x and y intercepts. But even if we don't think about doing that, if we are given the equation in slope-intercept form, there is another way to go about it. Because we are given the y-intercept, let's go ahead and plot that, 0, 7. So again, this was given to us. We were told this. Now we had to infer a little bit. We had to understand how the setup is giving us this information. 4 is the slope. 7 is the y-coordinate of our y-intercept. So we plot the y-intercept, And now using the slope here, the 4, we can use this slope here to tell us additional points. Remember, what are we saying the slope represents? It's the change in the y variable with respect to the x variable. Well, this just says 4. Well, what that means is for every 1 unit we change in the x direction, we're going to change 4 in the y direction. And the way that we can visualize this too is the number 4 can actually be written as a fraction 4 over 1, right? 4 divided by 1 is just 4. So now we can see here that how do we represent this change? For every 4 units we change vertically, we'll change 1 unit horizontally. So start here at this point. This 4 says, let's move up 4 units. And this 1 says, let's move to the right 1 unit. Again, move up 4 units, move to the right 1 unit. We can continue this pattern as long as we like. Now, again, I want to be able to get it in scale to the picture here. So how could we go about this in the opposite direction? Well, if the slope tells us that we are increasing 4 units for every 1 unit we move horizontally, let's kind of backtrack that. How could we have gotten to here? If we move up 4 and to the right 1, let's reverse that path and now move down 4 and to the left 1. Again, reversing that path, moving down 4 and to the left 1. We see now that we have a better idea of our graph that's within our range. And we have the graph of our line. Notice again that our line is moving. As we look left to right, our graph is increasing. It's increasing. Why? Because our slope is positive. Our slope is 4. It's a positive number. Therefore, we do have an increasing line. We are walking up the mountain. Could have used the x and y intercepts. Very easy to do, right? Plug in the zeros, solve for the variables. You'll have your x and y intercepts. But if it's given to you in this slope intercept form, y equals mx plus b, or what we're going to start looking at in our function notation, here is our linear function, where the slope is 4, the y-intercept is 0, 7. And again, getting into this idea of evaluating, we could also find these additional points by plugging into our function. Look where -1 is. What is the function value, or what is the y value when x is -1? Let's feed it through our function. When x is -1, what is our function equal? -1 times 4 is -4. -4 plus 7 is +3. So we see here at -1, if we move up 3 units, we're going to get that point right there. We could even be a little bit trickier about this, and let's look at a fraction. Let's say 1/2. What about feeding a fraction into the function? Remember that functions deal with real numbers. They don't have to be whole numbers and integers every single time. We can work with fractions. We can work with irrational numbers. Generally, it's easier to work with fractions and integers. So you will normally see integers and fractions being fed through functions. What happens if we have 1/2 here? Well, 1/2 times 4, or half of 4 is 2. 2 plus 7 is 9. So if I come over here just halfway to the 1 unit, halfway, and move up 9 units, you see here, there's the 9th number. I hit that point right there. And I can continue doing this because why? There are an infinite number. There are an infinite number of ordered pairs that make up this line here, which means there are an infinite number of solutions for this linear equation. And for graphing this function here, make sure it's solved for y, and now we can exchange the y variable and write f of x because y depends on x, so we use the function notation. And then from there, we can evaluate our function. The word evaluate means just plug a number in for x. If I plug in -1, my function equals 3. If my function equals 3, that means the y coordinate is 3 when the x coordinate is -1. So in this video here, we're going to take a look at number 27. If I take a look in the book, give me one moment, please. This is actually on page 31, 1.3 exercises. And we're seeing here, we're being told to find the slope of a line. It says here, find the slope of the line passing through the pair of points. We're actually going to take a look there at number, let's say number 29. Let's take a look at number 29. It says we have the ordered pair 3, negative 4. And we have the ordered pair 5, 2. Okay, so again, first things first, we're working with the information given to us. I know we haven't gone over the definition for slope yet. Hopefully you have seen our formula for slope before. As we've been saying this entire time, what does slope mean? I don't want to think about it in terms of a formula. Slope represents the change in one variable with respect to the other variable. We want to know there's a relationship between two variables, two sets of numbers, two ideas. Whether that's cost and unit production, you can represent that by a quantity. You can find a relationship between those quantities. In this case here, we are generalizing everything, and we just call it, hey, there's a set of numbers, call them X. There's a set of numbers, call them Y. Find a relationship using the XY plane. So with this here, we're given the information. There's two ordered pairs. What can we do with two ordered pairs at any time? We're being told to find the slope of a line. Euclid said you can draw a line between any 2 points in space. These are the 2 points given to us. Ordered pairs are points on a graph. Let's go ahead and graph these 2 points. So ordered pair 3, negative 4. Think about it again. This ordered pair has got to be in any of these 4 quadrants. Remember quad because think about quad skates. You got 4 wheels. You have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Every ordered pair in quadrant 1 contains positive X and Y coordinates. In quadrant 2, we have negative X coordinates and positive Y coordinates. In quadrant 3, we have negative X coordinates and negative Y coordinates. And in quadrant 4, positive X coordinates and negative Y coordinates. You can understand why they're positive or negative in each case. If you're over here in quadrants 1 or 4, you had to move to the right, so the X's are positive. If you move to the left over here, the X's are negative. If you move up, the Y's are positive. If you move down, the Y's are negative. Looking at 3, negative 4, I know I'm in this quadrant. I move to the left 3 units. I move down 4 units. And let's go ahead and even give these names. Why not? Let's call that point P, right? Let's just say point P has this ordered pair of coordinates. And let's call this here, let's call that point Q. All right, so I just graphed point P just to give me an idea of which point that is out in space. What about 5, 2? They're both positive, so it must be in quadrant 1. I move to the right 5 units, and I move up 2 units. So here is point Q. Now again, those are the only 2 points I need in order to graph this line. We're trying to find the slope, but we're going to go ahead and find everything. We're going to go ahead and just do it all in this one problem here. I got 2 points. I know these 2 points lie on some line out in space. I don't know what the line looks like. I'm about to find out what it looks like. But in terms of it algebraically, I don't know what that linear equation looks like. But we're going to find out what it is. So I get my straight edge from over here, my handy dandy meter stick, and I use it to draw a very straight line that passes through these 2 points. Now I am aware that this line that passes through these 2 points contains every single ordered pair solution for whatever equation we're about to determine. How do we know we can find the equation? Well, first thing we got to do, we got to find the slope. We have to find the slope. Remember that the slope is saying how is one variable changing with respect to the other. In other words, we have 2 variables here. We have the X variable and we have the Y variable. How are they changing with respect to one another? How can you compare 2 numbers? Well, if you recall back to earlier algebra and maybe elementary intermediate algebra, ratios. A ratio is a comparison between 2 numbers. Writing a number as a fraction, you're able to compare the top number to the bottom number. If you cut a pizza into 8 slices and you eat 3 slices, you're comparing those 3 slices to the 8 slices that were cut. Because if you cut that pizza into 16 slices, those 3 slices don't look too big or as big anymore, right? But if you eat the 3 slices relative or compared to the 8 total, you ate 3/8 of the pizza, there's a comparison there, 3 out of 8, 3 compared to the 8 slices. So that's all a fraction is. It's a ratio. It gives you an idea of the top number relative to the bottom number. That's what slope does here as well. What we're going to see is, what is the change in this variable, the word change, the change in the y variable versus the change in the x variable. So it's actually kind of neat. I want to show you that there is this Greek letter here, or this Greek symbol, called delta. Delta refers to the change in a value. And in this case here, for the slope, we are looking at measuring the change in the y variable versus, or divided by, because we want to set up a ratio or a fraction, divided by the change in the x variable. This will give us our slope, which is represented by the lowercase m. But how do you find the change in the y variable? What does that mean? How do you find out how the variable is changing? Think about it in terms of your bank account. You had $20 in your bank account, and overnight you got paid, and now you have $800 in your bank account. How did it change? It increased, right? There was some sort of value in between. To go from 20 to 800, what was the change there? Oh, you were added in $780. Well, how did you find out that? Well, you took the 800 and you subtracted the 20 to get 780. And that's how we're going to find the change in the values here as well. Recall the formula for slope says, if you can determine the difference in the y values, let me go ahead and I'll pop this full view back up. The change in the y values, y2 minus y1, so in other words, subtract the y coordinates and divide that by the subtraction of the x coordinates. That is how we find slope. Slope is a measure. Slope is a number. It's just a number. When we say what is the slope, it's not 4x, right? It's just 4. It's just that quantifiable number. If I had to give a number on something or a measure on something, right, it's just going to be quantifiable. So those numbers, those quantities are going to come from the ordered pairs. We know that these two ordered pairs lie on this line. If we can find the slope between these two ordered pairs, that slope, that rate of change, that change of the variable versus the other variable, that's going to be the same for any two ordered pairs that is on this line. We saw it before. I was asking you, can you notice the pattern? Notice how as the x increased from 1 to 2 to 3, notice what the pattern of the y variable was doing. It had a constant change. One of those patterns, it decreased by 3 every time, or it increased by 2. That's the slope. That's what we're trying to find there. We're trying to find the slope. How is this variable increasing or decreasing versus this variable? Now again, I ask you this question. What is our line doing? Is our line increasing or is it decreasing? That will give us an idea of what the slope should equal. And in this case here, our line is increasing. So this value here should most definitely be positive. It should be a positive value. Let's see if we get that. How are the y values changing differently? This ordered pair here, we have 5, 2. This ordered pair here, we have 3, -4. To find the change in the y coordinates divided by the x coordinates change, notice here, it doesn't tell you specifically which ordered pair to plug in. It just says these two numbers here have to come from the same ordered pair, and these two numbers here have to come from the same ordered pair. Make sure, it's very important that the y coordinates go in the top and the x coordinates go in the bottom. The way that I look at this picture, right, this is kind of like, the q is kind of like my second ordered pair, just the way that I named it, p comes before q. So I'm going to use these as my x2, y2, and I'm going to use this as my x1, y1. So in our formula here, to find slope, y2 minus y1, 2 minus -4. 2 minus -4. I'm going to put this in parentheses right here, and just as all math teachers will tell you to do this, if you have a subtraction next to a negative, that's going to get confusing. Remember that when you subtract a negative, we're going to switch these signs anyways. If you subtract a negative, you're actually going to be adding that positive. And the way that works is just ideally think about it in terms of math, right? You can't subtract -$3 because -3 isn't a physical thing. So abstractly speaking, if you subtract a negative, it's just the same as adding the positive. So 2 minus -4 is 2 plus 4, which is 6. But we'll get there in a second. X2 minus x1, 5 minus 3. All right. So what is m here? As we stated, 2 plus 4 is 6. 5 minus 3 is 2. This tells us here that between these 2 points, notice that to go from -4, right? To go from -4 to 2, we had to go up 6 units, right? To go from -4 to 2, we had to go up 6 units. To go from 3 to 5, we had to move to the right 2 units. So you see this nice, beautiful Pythagorean right triangle. It tells us what that measure is. Moved up 6 units, moved to the right 2 units. So that ratio of 6 versus 2, we moved up 6 units vertically versus 2 units horizontally. That's the relationship. That's the ratio. 6 per 2. When you say per, right, miles per hour, you're dividing. 6 per 2, or 6 divided by 2, which we simplify down to 3 over 1. And 3 over 1, we simply write as 3. What does the slope of 3 mean? The slope of 3. It's positive. 3 is a positive number, so our line does increase. It also says that the y variable is going to change 3 units for every 1 unit change in the x. And that means that the x, it's moving to the right. As the x moves to the right 1 unit, we move up 3 units. As the x moves to the right 1, we move up 3. What does the slope also tell us? Using this slope of 3, we can find any point we want on here. Let's say we start right here, we move up 3 units, and we move over 1. We hit something right here. What happens if you move up 3 here? That becomes -1. If you move to the right 1, this becomes +4. Just using the slope of 3, we found another ordered pair that lies on this line. 4, -1. Somewhere right there. Just by using the slope, we can locate as many ordered pairs on that line that we want. What is the slope? The slope is 3. That is the rate of change. Every 1 unit increase on the x-axis, for every 1 unit we move to the right, we move up 3. For every 1 to the right, we move up 3. For every 1 to the right, we move up 3. That's what the slope is telling us there. Now here's the fun part. My question to you now is, what's the equation? We know that this line here, this line contains these 2 points, and subsequently when I looked at it, it also contained this one. We just found, using the formula for slope in 1.3, that the slope the slope is 3, or m equals 3. It's just no point in writing out words, so we use the symbols and the numbers and stuff like that. So I'll go ahead and erase that. Slope equals 3. So somehow, some way, this is the information we have. We have the slope is 3, and our line goes through these 2 points. Is that enough to find a linear equation? And the answer is yes. Let's use the formula for slope-intercept. Y equals mx plus b. How can we use this? How are we going to use this to find our linear equation? Well, it's actually pretty interesting because we already know what m is. M is equal to 3. So our equation, when we have it in slope-intercept form, this value, we already know what it is. It's this. So I'm going to go ahead and change that. So what we notice here is that if we can determine this value for b, we will have our linear equation. Let's find out what b is, but how do we do that? How do we find out what b is? Well, it's simple. What did we say these ordered pairs were? What do we call them? Right? We know that these 2 ordered pairs lie on this line here. They make up the graph. And we're trying to determine what this equation is that has these 2 points. Remember that we called them ordered pair solutions. They are solutions to whatever the heck this equation is. So let's use them as solutions to find the value of b. And I'm actually going to use this ordered pair here. We'll use both. Well, let's start with 5, 2. All right, what is 5? That's our x coordinate. 2 is our y coordinate. So taking 5 and plugging it in for x, and taking 2 and plugging it in for y, we can actually solve for b. And when we solve for b, we'll take that number, back substitute it, we will have our equation. Let's try it out. 2 equals 3 times 5 plus b. Notice again, I took this ordered pair, I grabbed the coordinates, and I plugged them into x and y respectively. Now we're going to solve for this lonely variable b. 3 times 5 is 15. So 15 plus b equals 2. To get b by itself, because we are adding 15, let's subtract 15. What does b equal? 2 minus 15. b is negative 13. If our slope is 3, and the value of b, which is negative 13, what is our linear equation? Y equals 3x minus 13. Notice what the minus 13 tells us. Our y-intercept is the ordered pair 0, negative 13. So this line, had we extended it all the way out here, right there, where this line, and again, remember, the line is never ending, it's infinite. This will continue on and on until infinity. Just imagine that line just running out in space. It's never going to stop. Same thing in this direction. It is never ending. It is never going to stop. Remember what we said about the domain. The domain of a line is all real numbers. Every real number from negative infinity to positive infinity can be plugged in to this equation right here. 3x minus 13, where the y-intercept is 0, negative 13. Well, what's our x-intercept? Find the x-intercept, set y equal to 0, and solve. Add the 13 divided by 3. We have our x-intercept as well. Again, how do you find the x-intercept? Set y equal to 0, solve for x. Add the 13, divide by 3, 13 over 3. That is our x coordinate. Lastly here, what do you want to do? You want to rewrite this once you solve it for y. You want to rewrite the y as f of x. And you have 3x minus 13. Now, I do want to show you that had you chosen the other ordered pair, you would still get this same exact equation. Let's go ahead and try that out. So y equals mx plus b, where m equals 3x plus b. Let's not plug in the 5 and the 2. Let's plug in the 3 and the negative 4. The 3 gets plugged into x. The negative 4 gets plugged in to y. Let's see what happens there. Negative 4 equals 3 times 3, so that's 9. So we get 9 plus b. To get b by itself, let's subtract 9 from each side. What does b equal once again? b equals negative 4 minus 9, which is negative 13. So either way you look at it, you will get the negative 13 there. Therefore, mx plus b is 3x minus 13. 3x minus 13. And so again, the neat thing is that once you have it in the function notation, I said before the solution we got was this, I found this extra ordered pair using the slope of 3, right? We move up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, and we can keep finding ordered pairs. But also notice that had we evaluated our function at 4, in other words, what is f of 4? F of 4 means we take 4, plug it into x, and see what the function is equal to. What is our output? 4 times 3 is 12, minus 13 is negative 1. So notice that when we evaluate a function, f of 4 equals negative 1. This is our x coordinate, and whatever the function equals, that is our y coordinate. In a lot of textbooks, you will see that they will draw this xy plane. This is your x variable, and up here, the y, they sometimes replace this with the f of x notation. It's just the idea that whatever you get out of the function, that is your y coordinate. And lastly here, because you will see it, so I do want to bring it up. I just showed you how to find the linear equation using the slope-intercept formula. If you recall way back when, there was also the point-slope formula, which is exactly what it sounds like. You use a point and you use the slope, just like what we did. We used a point and we used a slope to find the value of b. Another thing you could do here is use the slope and use the point for point-slope. Point-slope formula says take y and subtract a y coordinate, and this equals our slope times the difference of x and any x coordinate. Well, this actually is kind of familiar because if you think about this, if I take this here, this x minus x1, and I divide it on each side, well, that's just our formula for slope. So if you take this formula here for slope and just get this bottom over here and multiply it to the side, we get our point slope formula. And the point slope formula we can use anytime we have one point and one slope, just like what we did previously. But previously I used the slope intercept formula. Here we can use point slope and solve for y directly. There is no back substitution. You plug this directly in, solve for y, you're done. Again, we get to choose which ordered pair do you want to work with. I'm going to work with this one because the numbers are positive. It's easier to work with positive numbers. Y minus the y coordinate, y minus 2. This equals our slope m times x minus the x coordinate. So plugging in the x and y respectively, notice again, there is a subtraction going on here. These are positive numbers, but these positive numbers are being subtracted. So we're going to start off here. Notice there's a parentheses. The order of operations says get rid of parentheses first. So we'll distribute the 3. Get 3x minus 15. This equals y minus 2. And as you see here, to get y by itself, we're going to add the 2 to each side. So here we have y alone. On the right-hand side, where does the 2 become added? Where does it get grouped into? Remember, like terms. Where can we add the 2? To the negative 15. Once again, using our point-slope formula, we get the same exact linear equation as we should. There's something neat about these linear equations. It's a one-to-one property. In other words, for this linear equation, or for example, changing the notation, for this linear function, there is one and only one graph for this linear function, and it's this graph here. And for this graph here, there is no other function that represents this line other than this one right here. In this next one, we're going to look at problem number 30, finding the slope of the line between these two given points. Number 30, we have 1, 2, and negative 2, 2. Again, I'm going to call this, we'll call them point P and point Q. We're given the 2 points. Go ahead and graph it. For 1, 2, negative 2, positive 2. Again, all we need is 2 points to graph a line. Now, as we look at this graph, what do we notice about the line? What is different about this line than other lines we've seen so far? And that answer is exactly right. It is flat, right? There is no tilt in the line. It is completely straight across. It is as horizontal as the x-axis. So there's going to be something different about this line because it's not increasing, so the slope is not positive. It's not decreasing, so the slope is not negative. So what is the slope? Let's take a look at it numerically speaking, algebraically speaking, using the formula for slope. The change in the y coordinates, again, if this is my x1 and this is my y1, this is my x2, this is my y2. y2 minus y1 is 2 minus 2. x2 minus x1, negative 2 minus 1. Huh. What number do I get there? What's my ratio? It says, for these particular 2 points, when my x values move 3 units to the left, my y value doesn't move at all. What does that mean? When my x values change, right, notice that as we went from here to here, or as we go from here to here, as the x values move, are the y values moving at all, or are they staying the same? Notice there is no increase, right? There is no increase, there is no decrease. It's just steady and flat. Well, that's because when you look at the measure of the slope between these 2 points, and therefore any point that's on this horizontal line, I can choose a point way over here, I can choose a point way over here. It doesn't matter if I look at T versus S or T versus Q. Any 2 points on this line here, if I look at the measure of their slope, how is the y variable changing with respect to the x? Notice here that this y variable, the y coordinate is exactly the same. It's not changing at all. The y coordinate has no change at all. It has 0 change. Notice here that when you subtract the 2 numbers, you get the value of 0. If you have a fraction and 0 is in the fraction, it is important to note where does the 0 occur. Is it in the numerator or is it in the denominator? If your 0 is in the numerator, like what we have here, 0 divided by negative 3 is 0, right? As a fraction, you can have 0 in the numerator. If I have $0 and I wanted to divide it out to my family, divided by 4 people, everyone gets $0. But the converse of that, if I have $4 and I divide it by 0 people, well, I'm not handing anybody anything. There's no idea, there's no logic behind that to divide a group by 0. There's no idea behind that, so it's undefined. When we say slope is undefined, that's when there is no change in the x variable. In other words, your graph is vertical. If you have a vertical graph, notice that you are moving vertically. So the y coordinate is changing every single time, right? When you move up and down, your y coordinate is changing. But if you can't move from left to right, if you are straight up and down, there is no horizontal movement. Therefore, the change in the x coordinate is 0. But for this particular problem here, there is no change in the y coordinate. We have a horizontal line. The slope of every single horizontal line is in fact 0. Now, if you take a look there, let's see, number 33 at the very bottom of the page. Number 33 gives us 2 ordered pairs. But notice that, again, before we even write anything down, notice the relationship between those 2 ordered pairs. They have the same exact x coordinate. So notice that the y coordinate goes from negative 3 to negative 5. It moved by 2 units. From negative 3 to negative 5, there was a 2-unit shift. But what did the x coordinate do? It didn't do anything. It didn't move at all. So as the y coordinate moved vertically, the x coordinate did not move. This is going to be a vertical line. We can graph it. Negative 8, negative 3. Move out 8 units. Move down 3 units. We have negative 8, negative 3. The next point, negative 8, negative 5, says move out 8 units, move down 5 units. When the x coordinates do not change, for example, number 33, this is number 33. When the x coordinates do not change, what is our slope? Actually going to be undefined. Let's see why. We have to use the algebra to show that the slope is undefined. So our first point, negative 8, negative 3, negative 8, negative 5, changing y coordinate from negative 5 to negative 3. The change in the x coordinates, negative 8 minus negative 8. So negative 5 minus negative 3 is negative 5 plus 3. Negative 5 plus 3 is negative 2. Negative 8 minus negative 8 is actually negative 8 plus 8, which is 0. Again, we have a fraction here. divided by 0. We cannot divide by 0. This is not okay. 0 can be in the numerator, it cannot be in the denominator. This is undefined. So every single vertical line, the slope m is undefined. And that's something to remember for our slope. Increasing lines have a positive slope. Decreasing lines have a negative slope. Flat